This is section 4.4, the Isosceles Triangle Theorems. We're going to take a moment to focus on just isosceles triangles, triangles in which there are two congruent sides. Two definitions before we begin. In an isosceles triangle, we call the two congruent sides legs, and we call the third side the base. So the two congruent sides in the isosceles triangle are called the legs. The third side is called the base. So on this blue triangle I've drawn on the right, I've labeled these two sides as legs on the left and the right because those are equal, which I know by these red hash marks. And the third side at the bottom is the base. We call the angle at the top the angle between the two congruent sides, the vertex angle. We call the two angles at the ends of the base angles. The base does not have to be pictured at the bottom of the triangle. It only is if I have the triangle standing up like that, where the two congruent sides are on the left and the right. But on this green triangle I've drawn here on the left side, my congruent sides are on the top and the bottom. So those are still the legs. This is a leg, and this is a leg down here. And the base is this over here. So then my vertex angle is here because it's between the two legs, and then the base angles are here and here, the two angles at the ends of the base. Okay, now that we have the terminology, we can talk about these triangles. Think about taking a sheet of paper. I'm going to do this with my sheet of paper. We've got a full sheet of paper, and I folded it in half. And I'm going to cut this paper to make a triangle. So I'm going to cut diagonally up like this. There we go. And I've got a triangle. And if I open it up, I have another triangle. But that bigger triangle is twice the size of the smaller one. It's the smaller one doubled, right? And I know because I cut them together that these two sides are congruent. I cut this side and this side together because I had them folded over, so they have to be the same length. And these two sides at the bottom are clearly the same length. Sides in the middle are the same, so that's the same length. It's equal to itself. So I actually have, when I look at these two triangles next to each other, I have two congruent triangles, side, side, side. But big triangle is isosceles, because this side was equal to this side because I cut them together. In that isosceles triangle then, since these two smaller triangles are congruent, now the corresponding parts of those triangles are congruent, which means that I know this angle and this angle are congruent, because they would correspond with each other in these two congruent triangles. I can tell they correspond because when I fold them over, they match up. Okay, so these two angles that are right now matched up must be equal in length and measure, so they are congruent to each other. Those are the two base angles of my bigger isosceles triangle. So I've now just discovered that those two base angles are congruent. It turns out that's always the case in an isosceles triangle. So we're going to state that as a theorem. A theorem that's so important to give it a name. We call it the Isosceles Triangle Theorem, for obvious reasons. It says, if two sides of a triangle are congruent, then the angles opposite those sides are, well, what did we just say about them? We said they were congruent. If two sides of a triangle are congruent, then the angles opposite those sides are congruent. So in this purple triangle I've drawn here, it's isosceles. I've marked AB and AC as being congruent to each other. I have those two hash marks. The angle opposite AB is angle C. The angle opposite AC is angle B. So according to this theorem, since AB is congruent to AC, angle C is congruent to angle B, because angle C is opposite AB, angle B is opposite AC. Now I could state those in the other order because it's symmetric. I could say angle B is congruent to angle C, so that order doesn't matter. The point is, the angles opposite those sides are congruent if those sides were congruent. So I can write that in a shortened form. If I'm stating this as a reason and a proof, I could either write Isosceles Triangle theorem, and that is fine, or I could write congruent sides imply congruent opposite angles. That's fine too, as long as we understand that it only works in a triangle. In a triangle, when we have congruent sides, then we have congruent opposite angles. Do you remember what a corollary is? A corollary is a theorem that is proven directly and very obviously from another theorem. So we have these three corollaries to the isosceles triangle theorem. First one says an equilateral triangle is also equiangular. We know an equilateral triangle is always isosceles, because equilateral means it has three congruent sides. Isosceles means it has two congruent sides. If it has three congruent sides, it certainly has two congruent sides. So the equilateral triangle applies to this isosceles triangle theorem. And we would be able, by taking different pairs of sides of that equilateral triangle, to get each of those three angles equal to each other. So an equilateral triangle is also equiangular, which is very, very useful. An equilateral triangle has three 60-degree angles, because we know an equiangular triangle has three 60-degree angles. We just said an equilateral triangle is equiangular. So in any equilateral triangle we have three 60-degree angles. The third one is less obvious. The bisector of the vertex angle is perpendicular to the base at its midpoint. The bisector of the vertex angle is perpendicular to its base at its midpoint. So let me draw that. Okay, I'm going to claim that's isosceles with those equal to each other. So the vertex angle is up here. The bisector of that will be a segment or a ray that goes halfway through that angle. It divides it into two congruent pieces. So this angle would have to be congruent to this angle, if I've just drawn the bisector. What this corollary is saying, that is perpendicular to the base, so we have a right angle there, at the base's midpoint. So this is congruent to that. So the bisector of the vertex angle is perpendicular to the base at its midpoint. Not a corollary we're going to be using very often, but it will show up. What is the converse of the isosceles triangle theorem? Remember, a converse just takes the hypothesis and the conclusion and swaps them. So, if this theorem said two sides of a triangle are congruent, then the angles opposite those sides are congruent. The converse would say, if two angles of a triangle are congruent, then the sides opposite them are congruent. And it turns out that converse is also true. So, if two angles of a triangle are congruent, then the sides opposite those angles are congruent. We can call that the converse of the isosceles triangle theorem, or I'll give you a shortened form of how to write it in a second. So in this triangle, I have angle B congruent to angle C. What this theorem says is that if angle B is congruent to angle C, then the side opposite angle B, which is AC, is congruent to the side opposite angle C, which is AB. So AC is congruent to AB. Another very useful theorem. If you have two angles of a triangle congruent, the sides opposite those angles are also congruent. It gives us a way to relate angles and sides of triangles. So in a shortened form, we could write congruent angles imply congruent opposite sides, which is the converse of the theorem we just had. Congruent opposite sides imply congruent sides imply congruent opposite angles. One corollary to this theorem: an equiangular triangle is also equilateral, which is the converse of the corollary we stated earlier. It said an equilateral triangle is also equiangular. So now if we know we have three congruent angles, we can take different pairs of those angles and know that the sides opposite those angles are congruent, so we can get that the whole triangle is equilateral. One example. Here I have an isosceles triangle. We see the two sides that I've marked equal with those hash marks. Find x. X is this angle down here. Well, I know this angle, the vertex angle, is 30 degrees. Since I have two congruent sides, I know the angles opposite those sides are congruent. So the angle that's x degrees is congruent to this other base angle up here. So that one is also x degrees. Now I know the three angles of the triangle add up to 180, so I can write this equation. 30 plus x equals 180. And I can solve that for x. 30 plus 2x equals 180. Subtract 30 from both sides. 2x equals 150. Divide both sides by 2. X equals 75 degrees. So remember, anytime we have a problem where we're trying to find x, we want to write an equation that involves x that we can then solve for x. So you're going to do that on your two immediate practice problems. Directions are: find the value of x. In the triangle on the left, the green one, we have two equal angles, so we know the sides opposite those angles are congruent. Use that to write an equation with 2x minus 4 and x plus 5 and solve that for x. In the triangle on the right, the orange one, we don't yet have any congruent angles or congruent sides. The side on the left is 42, the side on the right is 41, and the side at the bottom is x. But this angle on the left is 56, the angle on the right is 62. Your hint: find the measure of this angle up here. And then maybe you'll have some equal angles, and you'll have equal opposite sides, and you'll know whether x is 42 or 41. That is the end of section 4.4.